You have probably been told, at some point, that you are a cosmic accident, that the universe is enormous and indifferent, that it was never made with you in mind, a passing speck on a rock circling an ordinary star. Part of that is true, but here is what the story leaves out. When physicists measured the numbers built into the laws of nature, they found something no one expected. The nuclear force sits in a window only a few thousandths wide, and outside it there is no chemistry at all. Gravity is weaker than electricity by a factor with 36 zeros, and that weakness is the only reason stars burn slowly enough for life to have time to appear. The energy in empty space is smaller than our best theory predicts by a factor with 120 zeros, and if it were larger, the universe would have torn itself apart before the first atom. A dozen unrelated numbers, each on a knife edge, all pointing toward a universe that can hold you. So maybe you are not the accident you were told you were. Or maybe the truth is stranger than either accident or design. Get comfortable and settle in. Hit subscribe if you are new here, because by the end of this, the empty space around you and the ordinary star above you will feel less like an accident and more like a question no one can yet answer. Now, let's slowly ease into this. Part 1. Everything fits too well. Nothing about the universe had to allow you to be here. That is the quiet fact underneath everything we are going to talk about tonight, and it is easy to walk past without noticing, so let us slow down and sit with it for a moment. The universe could have been almost anything. It could have been a thin, cold fog of hydrogen and nothing else, spread out forever, never gathering into a single star. It could have been a churning sea of black holes, crushing every piece of matter before it ever had the chance to become anything. It could have flown apart so fast, in its first fraction of a second, that no two particles ever met again. Any of those universes would have been perfectly lawful. They would have broken no rule of physics. And in every one of them, there would be no atoms heavier than the lightest few, no chemistry, no planets, no warmth that lasts, and no one drifting off to the sound of a voice describing it all. Instead, we got this one. We got a universe that knows how to build carbon and oxygen and iron, that can hold them together in stable atoms, that can gather those atoms into stars and let those stars burn steadily for billions of years, and that can, given enough of that time, assemble some of that matter into something that wakes up and asks why. When you first hear that, it sounds like nothing more than good fortune, the kind of thing you might feel grateful for and then forget. But physicists have looked closely at exactly how this universe manages the trick, and what they found is not comforting in the way you might expect. What they found is that the whole arrangement seems to depend on a handful of numbers, and that those numbers appear to be balanced on the edge of a knife. Here is what I mean by numbers. When you write down the laws of physics, the laws themselves do not tell you everything. They leave blank spaces that have to be filled in by measurement. How strong is gravity, exactly? How strong is the force that holds a nucleus together? How heavy is an electron compared to the particles in the nucleus? How much energy is hidden inside empty space? Each of these has an answer, and each answer is a specific number, and here is the strange part. Not one of these numbers is predicted by any theory we have. We do not calculate them. We go out and measure them, we write them into the equations by hand, and then we treat them as simple brute facts about the world. They are the settings the universe happens to run on. It is worth pausing on how strange it is that physics contains numbers like these at all, because it was not always obvious that it would. For a long time, many physicists assumed that every quantity in nature would eventually be explained, derived from something more basic, until nothing arbitrary was left anywhere in the equations. The slow surprise of the last 100 years was the growing suspicion that this might not be true, that some numbers really do sit in the theory as raw values, unexplained and perhaps unexplainable from inside it. Paul Dirac, one of the founders of quantum physics, was so unsettled by certain of these numbers, and by odd coincidences among them, that he spent years chasing the notion that they had to be linked by some law nobody had found yet. Arthur Eddington filled pages trying to derive the strength of electromagnetism from pure reasoning alone, and got nowhere, as everyone since has gotten nowhere. The numbers refuse to be argued out of the equations. They simply sit there, measured and inserted by hand, as arbitrary today as when we first wrote them down. That is what makes the word tuned so loaded, and so worth handling with care. When we say a number is tuned, we are noticing two things at once. We are noticing that the number could apparently have been otherwise, that nothing we know forces it. And we are noticing that its actual value falls in a suspiciously narrow band, the band a universe would need in order to become interesting. Neither observation alone would trouble anyone. A number that could vary but does not matter is boring. A number that matters but could not have been otherwise is just a law. It is only when both are true at once, when a number both could have been anything and had to be nearly exactly what it is for us to be here, that you get the peculiar vertigo we are chasing tonight. So keep both halves of the word in mind as we go. Tuned means could have been otherwise, and tuned means had to be nearly exact. When I point to a dial tonight, I am always claiming both things about it at once, and you are entitled to check me on both. Ask each time whether the number really could have taken other values, and whether the window it fell into really is as narrow as I say. If either half fails, the tuning is not real. What makes this subject so hard to wave away is that, dial after dial, both halves keep holding. I want you to picture those settings as a wall of dials. Imagine a long control panel in the dark, and along it, a row of dials, each one governing a different law. One dial sets the strength of the nuclear glue that binds atoms. One sets the weight of the electron. One sets the pull of gravity. One sets the energy sleeping inside the vacuum. Every dial is turned to a precise position, and the universe you live in is the universe those exact positions produce. This picture of the dials is going to stay with us through everything that follows tonight, so let it settle in now, quietly, in the dark behind your eyes. A wall of dials, each one set to a value. Nobody yet able to say who set them, or whether anyone did. Now, the unsettling thing is what happens when you reach out, in your imagination, and nudge one of those dials. Physicists have done this on paper for decades. They take one of the constants, change it by a small amount, and then follow the consequences forward to see what kind of universe you would get. And again, the answer is the same. You get a dead universe. You nudge the dial a little one way, and stars never ignite. You nudge it a little the other way, and stars burn out before planets can cool. You move the vacuum energy off its setting by an almost invisible amount, and space tears itself apart before the first atom can form. The dials are not just set, they appear to be set inside windows, so narrow that almost any other setting would erase the possibility of complexity entirely. I want to be careful and honest with you right from the start, because this is a topic where it is very easy to slide from real physics into wishful thinking, and this channel does not do that. When I say the universe looks tuned, I am not saying it looks comfortable, and I am not saying it looks cozy or designed for our happiness. Most of the universe is lethal to us. It is nearly empty, nearly freezing, and mostly hostile. The tuning is a much narrower and much stranger claim than that. The claim is only this, that the universe permits complex structure to exist at all, anywhere, only because a dozen or so unrelated numbers happen to fall inside tiny ranges, and that physics right now cannot tell you why they fell there. That is not a warm feeling. It is a precise and slightly vertiginous observation about the machinery underneath reality. The astronomer Martin Rees tried to make this manageable for the rest of us. In a book he published in 1999, he argued that just 6 numbers, out of all the constants in physics, do most of the work of shaping the large-scale character of the universe, and that each one of those 6 appears to be tuned. We are going to walk through several of them tonight, one at a time, slowly, because the force of this idea does not come from any single number. A single balanced number could always be a coincidence. The force comes from the accumulation, from watching one unrelated dial after another turn out to sit inside its own narrow window, all of them somehow pointing toward the same result, which is a universe that can hold together long enough to produce something like us. So that is where we are going. We are going to move down the wall of dials, and we are going to look at what each one does and what happens when you touch it. And by the time we reach the end, the question will no longer be whether the universe looks tuned, because you will have seen that it plainly does. The question will be what that could possibly mean, and whether the answer is luck, or law, or selection, or something we do not yet have a name for. Tonight we start with the first dial, the one that decides something so basic that we almost never think about it. We start with the dial that decides whether there is any chemistry in the universe at all. Part 2. The first dial. Everything you have ever touched is held together by a number close to 7,000ths, and almost no one has ever heard of it. Let us start there, because it is the cleanest way into this. When 4 hydrogen nuclei come together inside a star and fuse into a single helium nucleus, they do not weigh, at the end, quite as much as they did at the start. A small fraction of their mass has vanished, converted into energy, which is the energy that makes the star shine. That fraction is about 0.7%. Written as a decimal, it is roughly 0.007. Physicists call it epsilon, and it measures how firmly the strong nuclear force binds particles together inside a nucleus. It is one of Rees's 6 numbers, and it is the first dial on our wall. 7,000ths does not sound like a number that anything important should depend on. But watch what happens when you touch the dial. Suppose you turn epsilon down just slightly from 0.007 to 0.006. That is a change of about 1 part in 7. In that universe, the nuclear force is a little weaker, and a crucial first step of fusion fails. To build up from hydrogen, you have to be able to bind 2 particles together and have them stay bound long enough to go further. Lower the strength just that little bit, and the very first rung of the ladder breaks. Hydrogen can no longer fuse into anything at all. You are left with a universe that is nothing but hydrogen forever. No helium to speak of, no carbon built later from that helium, no oxygen, no iron, no chemistry beyond the very simplest. A universe of a single element is a universe where nothing interesting can ever be made, because chemistry is the art of combining different elements, and there is only one. Try to picture what that hydrogen-only universe would actually be. It would not be empty. It would have plenty of matter, clouds of it, and gravity could still gather that matter together into large, dim balls of gas. But nothing would ever ignite in the way our stars do, because the fusion chain that powers a star cannot even begin. There would be no furnaces cooking up the heavier elements, so the periodic table would have exactly one entry. No carbon to build molecules, no oxygen to make water, no iron to make a planet's core, no nitrogen or phosphorus for anything to be alive. Just hydrogen, drifting and cooling, forever, in a cosmos that has all the raw material of a universe and none of the chemistry. That is the world on the low side of the dial, and it sits about 1 part in 7 away from the world we actually got. And this is the shape of thing we will meet again and again tonight, so it is worth naming plainly now. In ordinary life, and in most of physics, The world is forgiving. Nudge a quantity a little, and you get a slightly different outcome, not a catastrophe. What is strange about the constants of nature is how unforgiving they turn out to be. Small nudges do not give slightly different universes. They give dead ones. That brittleness, that sense of standing on a narrow ledge where a short step in any direction is a long way down, is the texture of the whole problem, and epsilon is only the first place we feel it. Now, turn the dial the other way, up from 0.007 to 0.008. You might think a stronger nuclear force would only help matters, but it does the opposite, and this is where it gets genuinely strange. With the force turned up that little bit, two protons can now bind directly to each other, forming something physicists call a diproton. In our universe, two protons cannot stick together on their own. The strong force is just barely too weak to overcome their electric repulsion, and that near failure turns out to be essential. Because if two protons could bind easily, then in the first few minutes after the beginning, when the whole universe was hot and dense enough for fusion, the hydrogen would not have sat there patiently for billions of years waiting to fuel stars. It would have burned. Nearly all of it would have fused almost immediately, and by the time things cooled, there would be little or no hydrogen left in the universe at all. Think about what losing the hydrogen would actually cost you. Hydrogen is one of the two ingredients in water, and every drop of water in your body, in every ocean, in every cloud, exists because free hydrogen survived. Hydrogen is the backbone of organic chemistry, the element that hangs off nearly every molecule biology uses. A universe with no leftover hydrogen is a universe with no water and no organic molecules, no matter how much time you give it. So the window on this one dial is roughly between 0.006 and 0.008. Below it, the fusion ladder never starts, and you are stranded with hydrogen alone. Above it, the hydrogen burns away and you are left without it. The actual value, the one our universe runs on, sits right inside that narrow band, close enough to both edges that a change in the third decimal place would ruin everything. I said we should always keep the numbers honest and grounded, so let me put the size of this window in perspective. When we say a value has to fall between 6,000ths and 8,000ths, we are talking about a target that is a small slice of the range it might have had. The strong force could, as far as any theory tells us, have taken a strength far outside that slice. There is no law we know of that forced it to land where chemistry needs it. It simply did. And notice what has already happened here, on only the first dial. We have not talked about anything exotic yet. No black holes, no vacuum energy, no beginning of time. We have only talked about whether the universe contains more than one kind of atom, and already the answer turned out to hang on a fraction balanced between two edges, with the drop on either side being total. There is a temptation, when you first hear this, to reach immediately for a conclusion. Some people hear it and feel certain it proves the universe was arranged on purpose. Other people hear it and feel certain it proves nothing at all, that any universe would look special to whatever happened to live in it. We are going to take both of those reactions seriously later, because both of them contain something true and something incomplete. But it would be a mistake to jump there now on the strength of one number. One tuned dial is a curiosity. It is the kind of thing a physicist files away and does not lose sleep over. If epsilon were the only balanced number in all of physics, this would be a footnote, not a mystery. The reason it is not a footnote is that epsilon is not alone. It is the first of many, and the ones that come after are governed by completely different parts of physics with no known connection to the strength of the nuclear force. That is the thing to hold on to as we move along the wall. We are not looking for one lucky number. We are looking to see whether the luck repeats in place after unrelated place until repetition itself becomes the thing that needs explaining. So keep epsilon in your mind, the 7,000ths that decides whether the universe has chemistry, and let us move to the next dial. Because the next one is the most famous coincidence in all of physics, and it involves a man who reasoned his way to the existence of a hidden law using nothing but the fact that he was alive to ask the question. Part 3. The number written in carbon. You are made of carbon, and carbon should be almost impossible to make. That sentence sounds like a contradiction, and following it to its resolution is one of the most remarkable stories in the history of science. Carbon is the sixth element, the one that biology is built around, the one whose ability to form long, flexible chains makes complicated molecules possible at all. Every cell in your body is a structure of carbon. And yet, when physicists first worked out how the elements are forged inside stars, carbon presented them with a genuine puzzle, because the obvious way to build it does not work. Here is the problem. Stars make heavier elements by fusing lighter ones, and the natural path to carbon runs through helium. A helium nucleus has 2 protons and 2 neutrons. Stick 2 of them together and you get a nucleus with 4 protons and 4 neutrons, which is beryllium-8. Add 1 more helium to that, and you reach 6 protons and 6 neutrons, which is carbon-12, ordinary carbon. Simple enough on paper. But there is a catch that seems to close the door completely. That intermediate step, beryllium-8, is not stable. The moment it forms, it falls back apart, and it does so almost unimaginably quickly, in about 1/10 quadrillionth of a second. That is a tiny sliver of time, far too short, it would seem, for a third helium nucleus to happen along and strike it before it disintegrates. The bridge to carbon collapses the instant it is built. In the early 1950s, the astronomer Fred Hoyle looked at this problem and made a leap that still astonishes physicists today. He reasoned backward from his own existence. Carbon clearly exists, he thought. I am standing here, and I am made of it, and so is everything around me, which means the stars must have found a way to make it despite the broken bridge. Since the ordinary reaction should fail, there must be something special about the carbon nucleus itself that rescues it, some feature we have not yet discovered. And he predicted, from that reasoning alone, that the carbon-12 nucleus must have a particular excited state, a specific higher energy configuration sitting at just the right energy to make the third collision resonate. Resonance, in this setting, means a matching of energies so precise that the reaction, which should almost never complete, instead completes far more often than you would ever expect. Let us sit inside this moment, because it is worth it. Picture Hoyle in 1953, working through the logic. He has no experimental sign of this energy state. Nobody has ever measured it. The nuclear physicists do not think it is there. He has only a chain of reasoning that begins with the fact that he is alive and made of carbon, and ends with a specific, checkable prediction about the inner structure of an atomic nucleus. He predicts that the level should sit near 7.68 million electron volts, a unit physicists use to measure nuclear energies. Then he goes to the experimental physicists at the California Institute of Technology, to a team led by Willie Fowler, and he essentially tells them to look for a level that theory says should not exist because his own body says it must. They are skeptical, but they look, and they find it. There is an excited state of carbon, sitting at 7.65 million electron volts, almost exactly where Hoyle said it would be, within a fraction of a percent of his prediction. The bridge to carbon is real after all, held open by a resonance that Hoyle deduced from nothing but the fact of his own existence. Let me hold you inside that picture a moment longer, because the physical scene is worth feeling. Far down in the core of an aging star, the temperature climbs to around 100 million degrees, and helium nuclei move fast, slamming into one another again and again. Most of those collisions come to nothing. 2 helium nuclei touch, make that flicker of beryllium, and it falls apart before anything else can happen, over and over, uncountably many times a second. But because the carbon resonance sits at just the right energy, and because the energy of the colliding particles at that temperature happens to match it, every so often a third helium arrives at the fleeting beryllium with exactly the energy needed to lock in, and carbon forms and holds. The match between the star's core temperature and the position of that energy level is itself part of the coincidence. Shift the level a little higher or lower, and the energies no longer line up, and the slow manufacture of carbon quietly shuts down. What makes this the cleanest case in the entire subject is that it is not vague. It is not a hand-waving sense that things seem convenient. It is a specific numerical prediction made in advance from the premise that observers exist and then confirmed in a laboratory to within a fraction of a percent. Whatever you end up believing about why the universe is the way it is, you have to reckon with the fact that once a scientist reasoned from the mere existence of his own body to a hidden feature of the atomic nucleus, and reality said yes. And there is a quieter lesson tucked inside the triumph, one we will need later. Hoyle did not find the carbon resonance by asking what the universe is made of and working forward. He found it by starting from the fact that observers exist and working backward to what the universe must therefore contain. That move, reasoning from our own existence to a feature of physics, is exactly the move that will return, in a far more sweeping form, when we try to explain the tuning as a whole. Here it produced a clean, confirmed prediction. Whether the same style of reasoning can carry the weight of explaining every dial at once is a much harder question, and we will come back to it with our eyes open. It is hard to overstate how strange and beautiful this is. A human being reasoned from the fact that he was alive to the location of a hidden energy level inside the atomic nucleus, a level no instrument had yet seen, and the universe turned out to agree with him. It remains the closest that physics has ever come to reading the tuning of the universe directly off the dial, out loud, and having reality confirm it. And the precision required is real. For stars to produce the amount of carbon we actually observe, that energy level has to fall inside a narrow band, roughly between 7.6 and 7.7 million electron volts. Shift it much outside that, and the resonance detunes, the reaction rate collapses, and the universe makes little or no carbon. The element that biology is built on hangs on the position of a single nuclear energy level landing inside a window a few percent wide. And then there is a second half to the coincidence, which makes it sharper still. Once you have made carbon, you face the opposite danger. Carbon can itself capture another helium nucleus and turn into oxygen. If oxygen had its own conveniently placed resonance just above the energy where carbon meets helium, then almost all the carbon a star made would immediately be converted onward into oxygen, and you would be left with very little carbon after all. But oxygen-16 does not have a resonance in that dangerous spot. Its nearest energy level sits just below the threshold instead of just above it, which means the carbon-to-oxygen reaction is not resonant, and carbon survives in abundance. So a universe with plenty of both carbon and oxygen, which is exactly the universe biology requires, needs one resonance to be present, in carbon, and another resonance to be absent, in oxygen. Two separate nuclear coincidences, pointing the same direction, toward a universe that can build living chemistry. Fred Hoyle himself was so struck by what he had found that he could not keep quiet about its implications. He later wrote that a common-sense interpretation of the facts suggested that some superintellect had, in his words, monkeyed with the physics, and that there were no blind forces worth speaking about in nature. Now, we are going to be very careful with statements like that, because a scientist's astonishment is not the same thing as a scientific conclusion, and we will come back later to what such reactions are worth and what they are not. Hoyle was expressing wonder, not proving a theorem, but you can understand why he felt it. He had used his own existence as an instrument, pointed it at the inside of a nucleus, and gotten a reading that came back true. So now we have two dials on the wall, and they are governed by the same underlying force, but they show up in completely different places. One decides whether the universe has more than one element at all. The other decides whether it can make the specific element that complex life is built from. Both sit inside narrow windows. Both would, if moved, produce a universe that could never have made you. But you might notice that both of these have been about the small scale, about the insides of nuclei. So let us now step back, all the way back, to the largest contrast in physics, the relationship between the weakest force and one of the strongest, because the next dial does not decide what the universe is made of. It decides whether the universe lasts long enough for any of it to matter. Part 4. The mercy of a weak force. Gravity is the weakest thing in the universe, and that weakness may be the reason you exist. This is one of those facts that sounds backward the first time you hear it, because gravity does not feel weak. Gravity holds you in your chair. Gravity keeps the moon circling the Earth and the Earth circling the sun. Gravity assembles galaxies out of scattered gas and crushes dead stars into black holes. It seems, from where we stand, like one of the great powers of nature. But that impression comes from the fact that gravity is the only force that always adds up. It only ever pulls, never pushes, so across the enormous mass of a planet or a star, its pull accumulates into something commanding. Measure it between two individual particles, though, and you find something almost comical. Gravity is feeble beyond belief. Let me give you the number, because the number is the whole point. Take two protons and hold them near each other. They feel two forces at once. They feel the electric repulsion between their like charges, pushing them apart, and they feel the gravitational attraction between their masses, pulling them together. Now, compare the strengths of those two pulls. The electric force between the two protons is stronger than the gravitational force by a factor of about 10 to the 36th power. That is a 1 followed by 36 zeros. To even approach a number that size in ordinary life, you would have to compare the width of a single atom to the distance across the entire observable universe, and you would still fall short. That is how much weaker gravity is than electromagnetism at the level of individual particles. Rees called this ratio n, and it is another of his 6 numbers, and it is the next dial on our wall. Here is why that staggering weakness matters, and why it is not a flaw but a gift. Because gravity is so weak, you need to pile up an enormous amount of matter before gravity can do anything dramatic with it. To gather enough hydrogen for gravity, to squeeze the center hard enough and hot enough to ignite fusion, you need something with the mass of a star, roughly a number of protons written as 1 followed by 57 zeros. That is why stars are the size they are. They are that large precisely because gravity is that weak, and they have to be that large to shine. And because it takes so much matter to light a star, and because the fusion inside burns slowly against gravity's gentle squeeze, a star can shine steadily for a very long time. Our sun has been burning for around 4.5 billion years, and will continue for billions more. That long, patient burn is the direct consequence of gravity being weak. Now touch the dial. Suppose gravity were not quite so feeble. Suppose you strengthened it so that n, instead of being 10 to the 36th, were only 10 to the 30th. That still leaves gravity far weaker than electromagnetism, 1,000,000 times weaker on this scale than it is in our universe, relatively speaking. But the consequences are severe. In a universe where gravity is 1,000,000 times stronger, stars can form from far less material, so they are much smaller, and a small star burns fast and furiously and dies young. Instead of shining for billions of years, a typical star in that universe might last only about 10,000 years before exhausting itself. 10,000 years is nothing. It is not enough time for a planet to cool and settle. It is not enough time for stable chemistry to unfold on that planet's surface. It is certainly not enough time for anything resembling the slow, patient process by which simple molecules become complicated ones, and complicated ones eventually become alive. Turn up gravity, and you buy a universe that flares and gutters out before it can produce anything that lasts. Let me make that strong gravity universe vivid for a moment, because the contrast sharpens what our own weak gravity buys us. Imagine a cosmos where gravity pulls 1,000,000 times harder at the level of particles. Stars there could form from a small mountain's worth of gas rather than a sun's worth, so the sky would be crowded with tiny, fierce stars, each one blazing and dying almost as soon as it lit, generations of them flickering past like sparks off a fire. A planet could barely exist before its star was gone. There would be no steady hearth to sit beside for billions of years, no long afternoon of a stable sun under which chemistry could take its unhurried time. Everything would be rushed, and rushed universes are barren, because complexity is a slow craft. It cannot be hurried into being. This is why physicists take the weakness of gravity so seriously that they have given the puzzle a name and treat it as one of the largest open problems in the field. They call it the hierarchy problem, and it is simply the question of why gravity is so absurdly feeble compared to the other forces, why the gap between them is a factor with more than 30 zeros in it, rather than something modest. There is no accepted answer. Some physicists have hoped that undiscovered particles or extra dimensions of space might explain it. So far, the experiments that looked for those explanations have come back empty. The weakness remains a measured fact with no derivation behind it. Another dial found in a particular position, and the position it was found in happens to be the one that grants the universe the long, patient reach of time. And notice how this dial reaches beyond chemistry into the very rhythm of the cosmos. The weakness of gravity does not only let stars live long, it sets the whole tempo of the universe, the unhurried pace at which galaxies assemble, stars are born and die, and heavy elements are seeded into space for the next generation to use. Everything grand and slow about the sky, the sense that the universe has all the time in the world, is the weakness of this one force made visible. Strengthen gravity, and you do not just shorten stars. You speed up the entire film until it blurs. And a blurred universe has no room in it for anything that has to be made slowly, which is to say, no room for anything like us. So the weakness of gravity is quietly one of the most important facts about our universe, because time is the ingredient that complexity cannot do without. Everything intricate in this world was made slowly. Stars forged the heavy elements over generations, living and dying and seeding space with their ash, from which new stars and planets condensed. On at least one of those planets, chemistry had billions of years to experiment before anything woke up. None of that is possible in a hurry. The universe needed to run the clock for a very long time, and it could only afford to run the clock that long because gravity is almost unimaginably gentle. The dial of gravity's strength is set not for drama, but for patience, and patience is what made us possible. And here is the part that should give you pause. Nothing in physics explains why gravity is this weak rather than merely strong. This is not a small gap in our knowledge. It is one of the largest open questions in all of physics, sometimes called the hierarchy problem, and it points exactly at this puzzle. Why is gravity so fantastically feeble compared to the other forces? We have no accepted answer. We can measure the weakness with great precision, but we cannot derive it. It is another dial that was simply found in a particular position, a position that happens to be the one that grants the universe the long, slow stretches of time that let complexity assemble itself. Move the dial, shorten the time, and the story ends before it begins. Notice what is accumulating here. We began with the strength of the nuclear force, deciding whether there is chemistry. We moved to the carbon resonance, deciding whether there is the element life is built from. Now we have the weakness of gravity, deciding whether there is enough time for any of it to come to anything. These are three entirely different pieces of physics. The nuclear force and the strength of gravity have no known relationship to each other. They are separate dials, governed by separate parts of the theory, and there is no reason one should care what the other is doing. Yet all three have turned out to sit in the narrow ranges that a universe would need in order to produce complexity. Three unrelated dials, three narrow windows, all pointing the same way. That is the pattern beginning to show itself, and we are only a third of the way down the wall. But if you think the tuning so far has been impressive, you have not yet met the number that broke physicists' composure. Everything up to now has involved windows a few percent wide, or a factor of a few. The next dial is tuned not to a few percent, and not to a few decimal places, but to a precision so extreme that physicists have called the situation the worst prediction in the history of science. It is the energy hidden inside empty space, and it is where the story stops being a curiosity and starts becoming something that can genuinely unsettle you. Part 5. The worst prediction ever made. Empty space is not empty, and the amount of energy it contains is the most finely balanced number ever discovered. Let us build up to why slowly, because this one deserves care. When you clear a region of space of everything, every particle, every speck of matter, every ray of light, you do not get true nothingness. According to quantum physics, which is the most thoroughly tested framework we have ever built, the vacuum still hums. It seethes with what are called virtual particles, pairs that flicker into existence and vanish again too quickly to be caught directly, but whose effects can be measured in the laboratory with great accuracy. This restless quantum vacuum carries energy. Even perfectly empty space has an energy of its own, woven into its fabric. That vacuum energy matters for the universe as a whole, because energy in empty space behaves in a peculiar way. It acts as a kind of pressure that pushes space to expand, a repulsion built into the vacuum itself. Physicists call this the cosmological constant, and it determines how strongly empty space drives itself apart. So, a natural question arises. How much vacuum energy should there be? We have the theory that describes the quantum vacuum, so we can try to calculate it, to add up the contributions of all those flickering virtual particles and arrive at a number. Physicists did exactly that. And this is where physics suffered what may be its single most spectacular failure. When you calculate how much energy the vacuum should contain, using our best theory of particles and fields, you get a number that is larger than the amount we actually observe, by a factor of about 10 to the 120th power. Let me try to make that factor real, though in truth it defeats the imagination. It is a 1 followed by 120 zeros. There is no comparison in ordinary experience that comes close. If you tried to count every atom in every star, in every galaxy, in the entire observable universe, you would reach a number with around 80 zeros, and you would still be 40 zeros short of this discrepancy. The prediction and the observation disagree, not by a little, not by a lot, but by the largest margin between theory and reality that has ever been recorded. This is why physicists, not given to drama in their technical papers, have called it the worst prediction in the history of physics. And here is what makes it a fine-tuning problem, rather than merely an embarrassment. If the vacuum energy really were anywhere near as large as the naive calculation suggests, the consequences for the universe would be immediate and total. That much repulsion built into empty space would have driven the universe apart so violently, so instantly, that matter could never have gathered into anything. No galaxies could form, no stars could form. No atoms could even stay near one another long enough to matter. Space would have flown apart into cold, sterile emptiness before the first second was out. For a universe to hold together long enough to build structure, the vacuum energy has to be almost perfectly small. Not zero, as it turns out, but fantastically close to zero, tuned down from the predicted value by that same factor with 120 zeros. I want you to sit with what that means, because this is the moment the whole subject changes character. The empty space threaded through your own body, the space between the atoms in your hand, between the particles in every one of those atoms, carries an energy that our best theory overestimates by a factor with 120 zeros in it. If that theory had been right, if the vacuum energy had come out anywhere near what the calculation says it should be, there would be no atoms in your hand, no you, and no universe with anything in it larger than a passing flicker. The most precisely balanced number known to science is the reason there is a you at all. Whatever set that dial, set it to a value so exact that if you wrote it as a decimal, you would write more than 100 zeros after the point before you reached the first meaningful digit. And no one knows what did the setting. This is different from the earlier dials, and it is worth being clear about how. The strength of the nuclear force was balanced inside a window a few percent wide. That is impressive, but a few percent is the kind of coincidence you can imagine shrugging off. The vacuum energy is balanced to more than 100 decimal places. Numbers do not usually appear in physics, tuned that finely without a reason behind them. When a quantity turns out to be exactly zero, we suspect a symmetry, some underlying principle forcing it to vanish. But the vacuum energy is not exactly zero. It is almost zero, tuned to that staggering precision, and then stopped just short at a tiny positive value that we have actually measured. A value of exactly zero, we might explain. A value this close to zero but not quite there is far harder, because it looks less like a law switching something off, and more like a dial turned, by hand, to a setting of extraordinary and specific delicacy. Physicists have not simply thrown up their hands at this. For years, the great hope was a principle called supersymmetry, which pairs the known particles with heavier partners in such a way that their contributions to the vacuum energy would largely cancel, one pushing up wherever another pushes down, leaving something much smaller behind. It was an elegant idea, and it would have tamed the number by a natural mechanism rather than by brute coincidence. But for supersymmetry to cancel the vacuum energy anywhere near completely, its partner particles would have to show up at energies our machines can reach, and the most powerful particle collider ever built has looked for them and, so far, found nothing. The cancellation, if it happens at all, is far from complete, and the enormous gap between prediction and reality remains. And this is why the vacuum energy, more than any other number, is the one that keeps physicists awake. The others you might, on a generous day, imagine as lucky rolls that happen to land well. But a roll that comes to rest on its edge and stays there, balanced to more than 100 decimal places, is not the kind of thing you shrug at. It is the kind of thing that makes a careful person suspect that either there is a mechanism we have completely failed to find, or that the value was chosen from among a great many, in the only sort of universe where a chooser of any kind, ourselves included, could be present to measure it. That suspicion is where the rest of the night is heading. It was this number, more than any other, that pushed a generation of physicists toward an idea many of them found deeply uncomfortable, an idea we are going to spend real time with later tonight. Because when you are confronted with a quantity tuned to more than 100 decimal places, and you have no mechanism that forces it there, you start to wonder whether the setting was selected rather than caused, whether ours might be one value among a great many that are realized somewhere, with us inevitably finding ourselves beside the rare setting that permits us to exist. That is a large and strange thought, and I do not want to rush into it. For now, only hold onto the vacuum energy as the sharpest single point in the entire case, the dial tuned so finely that it strains the meaning of the word coincidence. But even the vacuum energy, extreme as it is, concerns the laws the universe runs on, the settings of its forces and fields. There is another kind of tuning that is arguably deeper still, and it does not concern the laws at all. It concerns the way the universe began, the state it started in, before any of the slow story of stars and chemistry could unfold. And when you look closely at that beginning, you find a number that makes even the vacuum energy look modest. So let us leave the dials of the forces for a moment, and go all the way back to the first instant, to ask not why the laws are tuned, but why the beginning was. Part 6. The order at the beginning. The universe did not only start with the right laws. It started in an almost impossibly special condition, and that may be the strangest fact of all. Up to now we have been talking about the constants, the fixed settings of the forces and the particles. But there is a second category of tuning that has nothing to do with the strength of any force. It has to do with the state the universe was in at the very beginning, the particular arrangement it started from before it began to evolve. And it turns out that the initial state was not a generic, ordinary, likely sort of state. It was extraordinarily orderly, tuned to a degree that dwarfs everything we have discussed so far. Let me start with the gentler version of this, which is called the flatness problem. The overall density of the universe, how much matter and energy it contains in each region of space, determines the shape of space itself and the fate of the whole cosmos. There is a special value, called the critical density, that sits exactly on the boundary between two destinies. If the universe had begun a little denser than critical, its own gravity would have pulled it back together and collapsed it, in some cases within moments. If it had begun a little thinner than critical, it would have flown apart too fast for gravity to gather anything into galaxies. Only right at the critical value does space come out flat and expansion coast along in the gentle balance that allows structure to form. When we measure our universe today, we find it astonishingly close to that critical density. Space is flat, as far as we can tell, to within the precision of our instruments. That by itself might not alarm you, but now run the clock backward, and the coincidence sharpens into something severe. Because of the way the equations work, any tiny departure from the critical density grows over time. If the universe is even slightly off the balance early on, it becomes wildly off later. So for the density to be as close to critical as it is now, after billions of years of that imbalance being amplified, it had to be almost inconceivably close to critical at the beginning. When you trace it back to the earliest moment physics can describe, you find that the density had to equal the critical value to within about 1 part in 10 to the 62nd. That is, a decimal point followed by 61 zeros and then a 1. The universe balanced on the exact line between collapse and dispersal, and it did so with a precision of 62 digits from its first instant. Now, physicists do have a candidate explanation for the flatness, and honesty requires me to give it to you, because this channel does not hide the parts that push back. The idea is called cosmic inflation. It proposes that in the first tiny fraction of a second, the universe underwent a burst of staggeringly fast expansion, stretching by an enormous factor almost instantly. Stretching something that dramatically flattens it, the way blowing up a balloon to the size of the Earth would make any small patch of its surface look flat to anyone standing on it. So, inflation can take a universe that started with some curvature and iron it flat, which would explain why we measure flatness today without needing the density to have been fine-tuned by hand. It is a genuinely powerful idea, and there is real evidence for it. But notice what it does to the problem. It does not so much remove the tuning as relocate it, because inflation itself only works if it begins under rather particular conditions, and getting inflation started in the right way turns out to carry its own fine-tuning. The dial does not vanish. It moves to a different part of the wall, and that brings us to the deepest tuning of all, the one that even inflation cannot easily explain away, and it was pointed out most forcefully by the physicist Roger Penrose. It concerns entropy, which is a measure of disorder, of how many different microscopic arrangements would look the same from the outside. A high entropy state is disordered and ordinary and overwhelmingly likely, the way a shuffled deck of cards is. A low entropy state is orderly and special and overwhelmingly unlikely, the way a deck sorted perfectly by suit and rank is. Let me stretch the deck of cards a little further, because it carries the idea well. Shuffle a deck and you get some particular order, and that order is almost certainly one you have never seen before and will never see again. But you are not amazed by it, because nearly every order is a disordered one. There are a staggering number of shuffled arrangements, and only a handful of neat ones, so disorder is what you expect every single time. To find the deck sorted perfectly, all the suits together and each running cleanly from low to high would stop you cold, because that arrangement is one of the very few orderly ones out of an enormous number of possibilities. Now scale that intuition up, past anything a deck can hold, to the arrangement of everything in the early universe. A generic, likely beginning would have been disordered, high in entropy, the cosmic equivalent of a shuffled deck. What we actually got was the sorted deck, and not merely sorted, but sorted to that unwritable degree of precision. This is exactly why Penrose insisted that inflation, for all its power, cannot be the whole answer. Inflation can smooth the universe and flatten it, but a smooth, flat, hot beginning is still, in the accounting of entropy, an extraordinarily special and orderly starting point, not a generic one. To get inflation to happen in the first place, and to leave behind the low entropy order we observe, you seem to need to start from conditions that are themselves finely arranged. The order does not get created out of nothing by inflation. It has to be there, in some form, at the very outset. It is worth letting the scale of Penrose's number sink in, precisely because it cannot be pictured. Every other improbability we have met tonight could at least be written down. This one cannot. If you tried to print the number of zeros in it, using 1 0 for every particle in the observable universe, you would run out of particles long before you ran out of zeros to print. That is not a figure of speech. It is the literal situation. The orderliness the universe began with is more extreme than the entire contents of the cosmos could even notate. And that impossible orderliness is not some far-off abstraction. It is the reason your night has a yesterday and a tomorrow, the reason the past is fixed and the future is open. The most extreme tuning of all is also the most intimate. The universe today has a great deal of order left in it, stars still burning, structures still standing, which means it must have begun in a state of even greater order, extraordinarily low entropy. And Penrose estimated just how special that initial low entropy state had to be. The number he arrived at is beyond anything we have said tonight, beyond really any number that appears anywhere else in science. He calculated that the universe's initial state was special to about 1 part in 10 to the power of 10 to the 123rd. Take a moment with the structure of that. It is not 1 followed by 123 zeros. It is 1 followed by a number of zeros that is itself 10 to the 123rd, which is a 1 followed by 123 zeros worth of zeros. You could not write this number out if you used every particle in the observable universe as a digit. There is not enough room in the cosmos to print it, and that is the measure of how orderly, how finely arranged the beginning of the universe was, compared to how it might generically have been. Why does that initial order matter so much to you, personally, right now? Because it is the source of the arrow of time, the reason the past is different from the future. You can remember yesterday, but not tomorrow. A cup can fall and shatter, but never leap back together. Heat flows from hot to cold, and not the other way. All of that one-way character of time, the entire distinction between before and after that your whole life is built on, traces back to the fact that the universe began in that state of almost perfect order and has been gently unwinding from it ever since. If the beginning had been ordinary, high entropy, disordered like almost every possible beginning, there would be no arrow of time, no memory, no cause reliably before effect, and nothing that could live a life that moves forward. The most improbable condition known to science is quietly the reason your life has a direction at all, and physics has no accepted explanation for why the beginning was so orderly. So look at where we have arrived. It is not only that the laws of the universe are tuned, it is that the beginning was tuned too, and tuned far more severely, to a precision that makes even the vacuum energy look casual. The dials on the wall are not just the strengths of the forces. Some of them describe the state the whole thing started from, and those are set most finely of all. And now, having laid out this catalogue, having stacked up dial after dial, each in its narrow window, each unrelated to the others, all pointing toward a universe that can hold complexity, we have to stop and ask the hard question honestly. What does it even mean to call all of this tuned? Is that a real discovery about the world, or is it a trick of the way we are asking the question? That is where we turn next, and it is where the wonder starts to become a genuine problem. Part 7. Giving the coincidence a name. Before we ask why the universe is tuned, we have to ask something trickier, which is whether the word tuned is fair at all. This is the moment where a careful mind has to slow down, because it is very easy to be swept along by the accumulation of coincidences and forget to check whether we have set the question up honestly. So let us examine the reasoning itself, gently, and see what it really shows and what it quietly assumes. Because there is a serious objection lurking here, and taking it seriously is what separates real physics from comforting storytelling. The objection goes like this. Of course, you find yourself in a universe whose constants permit your existence. Where else could you possibly be? If the numbers had been set to values that forbid atoms and stars and chemistry, there would be no one there to notice the difference and complain about it. So the fact that we observe a life-permitting universe is not surprising at all. It is guaranteed. We could never have observed any other kind, because any other kind contains no observers. On this view, marvelling that the universe allows us to exist is a little like a puddle, marvelling that the hole it sits in fits its shape so perfectly. The fit is not evidence of design or of luck. It is just a condition of the puddle being there to notice anything. That puddle image is worth turning over slowly, because it captures both the force and the limit of the objection. The puddle wakes in its hole, finds that the hole fits it exactly, every contour matched, and concludes the hole must have been made for it. But of course, the puddle took the shape of whatever hole it happened to fill. The fit runs the other way. Point that back at us, and the argument says we did not find a universe made to fit our kind of life. We are the kind of life that formed in the universe we happened to get, shaped by its constants, rather than the constants being shaped for us. It is a genuinely humbling thought, and it may be exactly right. But notice where the objection quietly leans, because this matters for everything that follows. For the puddle argument to fully work, there has to be more than one hole. If there were only ever a single hole in all of existence, and it happened to have precisely the shape a puddle needs, you would still be entitled to wonder why. The reasoning diffuses our surprise only if reality is generous with holes, only if there are many universes trying many shapes, so that ours can be an unremarkable one among a multitude. Take that generosity away, leave just one universe, and the surprise comes flooding straight back. So hold this in mind. The move that seems to dissolve the whole puzzle by blaming our own bias as observers does not actually stand on its own. It is borrowing something it has not yet paid for. This line of reasoning has a name. It is called the anthropic principle, and it was given its clearest early statement by the physicist Brandon Carter in 1973 at a conference held, with some irony, To celebrate the 500th birthday of Copernicus, the man who taught us we are not at the center of anything, Carter drew a distinction that is worth keeping straight. The weak version of the anthropic principle simply says that what we observe must be compatible with our existence as observers. That is almost impossible to argue with. It is nearly a logical truth. The strong version makes a bolder claim about the universe being in some sense required to permit observers, and that version is far more contentious. For tonight, the weak version is the one that does the real work, and it is the one that turns the whole puzzle on its edge. Here is the image I want to give you for it, and it is one we are going to come back to before the night is out. Imagine an enormous wall, wider than you can see to either edge, and a rifle fired at it blindly, over and over, in the dark. Most shots hit bare wall, and nothing happens. But scattered across that wall are a few tiny targets, and every so often, purely by chance, a shot lands on one. Now suppose that only the shots that hit a target produce anything capable of looking back at where it landed. Every observer then, every entity that exists to consider its own situation, finds itself at the site of a hit and marvels at the accuracy of the shot that made it. But the accuracy is an illusion born of selection. There were countless misses. It is just that the misses produced no one to count them. Only the hits can look back. Hold on to that phrase, because it is the sharpest tool in this entire discussion. Only the hits can look back. If that is right, then the apparent tuning of the universe might not be a coincidence that needs explaining at all. It might be a selection effect, an inevitable consequence of the fact that we could only ever have found ourselves in one of the rare universes that permit us. The values of the constants would not be typical of what is possible. They would be typical of what is compatible with an observer existing to measure them, which is a very different thing. And this reframes the whole question. It moves us from asking, why is the universe tuned, as though a tuner must be responsible, to asking a subtler question. Is the appearance of tuning telling us something profound about reality, or is it telling us something about the unavoidable bias of any observer, who by definition can only ever wake up in a place that allowed it to wake up? But, and this is crucial, the anthropic principle by itself does not actually explain anything. It only diffuses the surprise, and only if something further is true. Notice the hidden requirement in the rifle image. For the selection argument to work, there have to be many shots. There have to be countless universes, or countless regions, actually out there with different settings of the dials, so that ours can be the rare hit among a multitude of misses. If there is only one universe, only one shot ever fired, then the fact that it landed on a target is not explained by saying observers can only exist at targets. With a single shot, hitting the tiny target on the one and only try is exactly as astonishing as it first seemed. The anthropic principle removes the mystery of the tuning only if reality supplies the many trials it quietly depends on. Without the many trials, it explains nothing. So the anthropic principle does not close the case. It sharpens it. It tells us that if there are many universes with varied constants, then the tuning we see is exactly what we should expect, no miracle required. And it tells us that if there is only one universe, the tuning remains as puzzling as ever, and we are owed some other account of it. Which means the whole weight of the question now falls on a single fork in the road. Either there is some reason the constants had to be what they are, a law we have not yet found that forced them, or there are many universes trying many values, and we sit inevitably beside a habitable one, or there is something else entirely, something we have not named, luck, law, selection, or something with no name. Those are the possibilities, and everything from here on is an attempt to walk down each of those roads and see how far it goes. Let us take them in turn, and let us start with the oldest and most hopeful one, the dream that has driven physics since long before anyone spoke of tuning. It is the dream that the numbers were never free to begin with. that when we finally understand the universe deeply enough, we will see that the constants could not have been anything other than what they are, that they are forced, fixed, written into the structure of reality with no room to wiggle. If that were true, the tuning would dissolve, because there would have been no choice to make. So let us follow that road, the road of necessity, and see where it leads. It leads somewhere its travellers did not expect. Part 8. The Dream of a Universe with No Choice. Einstein once said that what really interested him was whether God had any choice in creating the world. That single sentence captures the oldest and proudest hope in all of physics, and it is the first real answer to the fine-tuning problem, so let us give it the respect it deserves. The hope is this: perhaps the constants are not free parameters at all. Perhaps they only look like dials that could have been set to any value because we do not yet understand the machine well enough. And perhaps, when we finally find the deepest theory, the final and complete description of nature, we will discover that everything locks into place, that the strength of gravity and the mass of the electron and the energy of the vacuum all follow necessarily from the structure of that theory, the way the fact that a circle's circumference is a little more than 3 times its width follows necessarily from what a circle is. If that were true, it would be the most satisfying resolution imaginable, because it would mean there was never any tuning to explain. A tuned dial implies a dial that could have been set otherwise. But if the deepest law forces every constant to its exact value, then there was no otherwise. The universe had no choice. The numbers are what they are, because they mathematically could not have been anything else, and our existence simply rides along for free on the one and only universe that was ever possible. Einstein's question, whether God had any choice, would be answered with a clean no. There was only one way to build a universe, and this is it, and here we are inside it, because it is the only game there ever was. This dream is the engine behind the long search for what physicists sometimes call a theory of everything, a single framework that would unite all the forces and all the particles into one seamless description with no loose ends, and, ideally, no arbitrary numbers left to insert by hand. For most of the 20th century, this looked like the natural destination of physics. Each advance had unified things that once seemed separate. Electricity and magnetism turned out to be 2 faces of one force. That triumph is worth remembering because it is the source of the whole hope. In the 1860s, James Clerk Maxwell showed that electricity and magnetism, which had looked like separate phenomena, were really a single unified force, and in unifying them, he discovered that light itself was a ripple in that combined field. 2 mysteries became one, and a third was explained for free. That is the pattern physics fell in love with, and it kept recurring. In the 20th century, the electromagnetic force and the weak nuclear force, which govern very different processes, were shown to be 2 aspects of a single deeper force, merged at high energies, a result so important it earned a Nobel Prize. Each of these steps took things that seemed arbitrary and separate and revealed them as facets of something simpler underneath. So it was almost irresistible to imagine that this ladder of unification had a top rung. Keep climbing, keep merging the forces, and surely you reach a single final theory at the summit, one law from which everything else descends with no freedom left over. On that dream, the constants would not be inputs you measure, they would be outputs you derive, fixed by the structure of the final law. Paul Dirac and Einstein, and many who came after, carried some version of this hope, and it drove the field for generations. The whole point of a theory of everything was not merely to describe nature, but to leave nothing arbitrary in it, to answer Einstein's question about whether the universe had any choice with a firm and final no. There is a real beauty in that ambition, and it is worth honouring even now that it has run into trouble, because it is the same impulse that drove every genuine advance in the history of the subject. The conviction that the universe is, at bottom, simple and lawful and free of loose ends is what made people keep digging when the digging was hard. Nobody hoped for a final theory in order to be told that the constants are arbitrary after all. They hoped for the opposite, for a last equation so tight that reality had no room left to wiggle, so that the answer to why is it this way would finally be because it could not have been any other. That is the road of necessity, and we are about to watch it arrive somewhere it never meant to go. The zoo of particles turned out to be built from a smaller set of pieces following elegant rules. It seemed reasonable to hope that the final step would tie everything together so tightly that the constants would simply fall out of the mathematics, uniquely determined, no freedom remaining. The tuning would be revealed as an illusion, an artifact of our ignorance, dissolved the moment we understood the whole. The leading candidate for such a final theory for several decades now has been string theory. Its central idea is beautiful in its simplicity. What if the fundamental objects of nature are not point-like particles, but tiny vibrating strings? And what if the different particles we observe are just different notes, different modes of vibration of these same underlying strings? From that one idea, string theory promised to weave together gravity and quantum physics, which have stubbornly refused to be reconciled, and to do it within a single mathematical structure. For a time, many physicists hoped that string theory would be the fulfillment of Einstein's dream, the theory so constrained that it would permit only one possible universe, with the constants we observe emerging as the unique solution, forced and inevitable. And then string theory delivered the opposite of what was hoped for, and this is the twist that makes the story remarkable. As physicists worked out the consequences of the theory, they found that it does not point to a single universe with a single set of constants. It points to an almost unimaginable number of possible universes, each with different values of the constants, different particle masses, different force strengths, different vacuum energies. The theory has, built into it, a colossal number of possible stable configurations, possible ways for its extra structure to settle, and each configuration yields a different physics. Estimates for how many such configurations there are run to about 10 to the 500th power. That is a 1 followed by 500 zeros, a number so enormous that it makes the count of atoms in the observable universe look like nothing at all. Sit with the irony of that, because it is exactly the reverse of what everyone wanted. The theory that was supposed to explain why the constants had to be what they are, instead, produced a catalogue of nearly every value they could conceivably have been. It did not narrow the possibilities to one. It blew them open to a number beyond counting. The dream was a universe with no choice, a single forced solution. What string theory offered was a near infinity of choices, an immense range of allowed universes, of which ours is merely one particular selection. Whether this is a failure of the theory or a profound clue about reality is one of the live arguments in physics today, and reasonable physicists come down on both sides of it. Some see the enormous number of solutions as a sign that string theory has lost its predictive power and taken a wrong turn. Others see it as the theory quietly telling us something true and uncomfortable about the world. Because notice what that near infinity of possible universes does to our earlier reasoning. Remember the rifle and the wall, and the requirement hidden inside the anthropic argument that for selection to explain the tuning there must be many shots, many actual universes, trying many values. The dream of necessity was supposed to make that requirement unnecessary, by proving there was only ever one possible universe. But necessity, pursued to its leading candidate, turned around and handed us the many possibilities instead. It gave us, on paper, the enormous range of settings that the selection argument needs. The road of law, followed far enough, ran directly into the road of chance. And so we are pushed, almost against our will, toward the second answer, the one that many physicists resisted for as long as they could. The idea that the reason our universe is tuned is that there are countless other universes that are not, and we could only ever have lived here. We are pushed toward the multiverse. Part 9. The endless field of other universes. If there is not one universe, but an endless multitude of them, each with its dials set differently, then the mystery of the tuning does not so much get solved as evaporate. This is the second great answer, and I want to approach it slowly and fairly, because it is easy to caricature and easy to dismiss, and it deserves neither. The idea is not that physicists simply invented other universes to escape an awkward question. The idea is that two separate lines of physics, developed for their own reasons, happen to point toward the same startling conclusion, that our universe may be one bubble among a practically infinite number, each one its own separate cosmos, with its own settings of the constants. The first line comes from cosmology, from the study of that early burst of expansion we met earlier, called inflation. When physicists worked through the details of how inflation would unfold, many of them concluded that it does not happen just once and then stop cleanly everywhere. Instead, in many versions of the theory, inflation is eternal. It keeps going endlessly in the larger fabric of reality. Here and there, pockets stop inflating and settle down into calm regions, and each such pocket becomes a universe like ours, a bubble that cools and forms galaxies and stars. But between and around these bubbles, the frantic expansion never ceases, and it is always budding off new bubbles, forever. This is called eternal inflation, and it was developed out of the work of physicists, including Alan Guth, who proposed inflation in 1981, and André Linde and Alexander Vilenkin, who extended it. If it is right, then universes are not rare. They are constantly being born, without end. The second line is the one we just met, from string theory, with its enormous number of possible settings for the constants, that count of about 10 to the 500th power. Put the two together, and something clicks into place. Eternal inflation provides a mechanism for making an unlimited number of bubble universes. String theory provides the menu of different physics that each bubble might adopt when it settles. Combine them, and you get a reality in which universe after universe comes into being, each one drawing a different set of values for its dials from that immense menu. Most of them draw badly. Most get settings that forbid atoms or stars or chemistry, and they sit there, sterile and empty, or they tear themselves apart, or they collapse. But with an unlimited number of draws, some rare bubbles will happen to draw a life-permitting set of values. And in those, and only those, observers can arise to look around and wonder why their universe fits them so well. Let me take you into this picture directly, because it is worth feeling rather than only understanding. Close your eyes, if they are not closed already, and imagine you could rise up out of our universe and drift over the whole endless multitude of them, seeing each one laid out below you like a valley in an unbroken terrain that stretches past the horizon in every direction. You begin to move across it. You pass over a universe where gravity was drawn too strong, and everything in it has already collapsed into a crush of black holes, dark and silent. You drift over another that is nothing but thin, cold, hydrogen fog, spread out and structureless, never to make a single star. You pass one where the vacuum energy was drawn large, and it flew apart into emptiness before its first second ended, a universe that was over before it began. On and on it goes beneath you, billions upon billions of them, valley after valley, nearly all of them dead, each one a different throw of the dials that came up wrong. You keep drifting, and the failed universes keep passing beneath you, and their variety is itself a kind of lesson. Here is one where the nuclear force was drawn a touch too weak, and it never climbed past hydrogen, a cosmos of nothing but the lightest gas, cooling slowly toward the dark. Here is one where the ripples in the early matter were drawn too smooth, and nothing ever gathered, no galaxy, no star, just a thinning haze spread out past every horizon. Here is one where those same ripples were drawn too rough, and everything collapsed early into a crowd of black holes, a universe that is all gravity wells and no room for anything to live between them. Here is one that lasted a single second, and one that lasted a little longer and then folded back into a point. Each is lawful, each broke no rule. Each simply drew a set of values that led nowhere, and there was no one inside any of them to mind. This is the picture that eternal inflation actually paints, once you take it seriously, which is part of why so many physicists find themselves reaching for it even when they wish they did not. The frantic expansion never stops in the greater fabric. It is always spinning off new pockets, each one settling into its own physics, without end. Given endlessly many pockets and a huge menu of possible settings, every allowed combination gets tried somewhere, most of them uselessly. The habitable ones are a vanishing fraction, but a vanishing fraction of an unlimited number is still an unlimited number of living universes, scattered impossibly far apart through a mostly dead multitude. And in each of those rare living pockets, something eventually wakes up and looks around and finds the settings suspiciously perfect, never seeing the countless dead drawers that make its own good fortune ordinary. And then, quietly, you settle down into one narrow valley where the numbers came out just so, where the nuclear force is strong enough for chemistry, but not so strong it burns the hydrogen away, where gravity is weak enough to buy billions of years, where the vacuum energy is almost perfectly small. And as you look around this rare and gentle valley, you realize you have been standing in it the whole time. This is the one. This is home. Not because it was chosen for you, but because you could only ever have woken up in a valley like this one. That is the multiverse answer, and you can see how completely it dissolves the puzzle. On this view, there is nothing to explain about the tuning. In the same way, there is nothing to explain about why a lottery has a winner. Someone wins every lottery, and the winner, staring at the improbable ticket, may feel singled out by fate, but the explanation is simply that enough tickets were sold. Our universe is the winning ticket, and the reason we hold it is that we could not have existed to hold any other. The rifle fired at the wall countless times, and here we are at one of the rare hits, because only the hits can look back. The tuning was never a message, it was a selection. But I promised you honesty, and honesty requires saying plainly what this answer costs, because it is not free. To make the tuning ordinary, the multiverse asks you to accept an almost unlimited number of other universes that you can never see, never visit, never detect, and quite possibly never confirm exist at all. That is an enormous thing to take on faith, or at least on inference, and many physicists are deeply uneasy about it, for reasons we will come to. It solves one problem by conjuring a reality vastly larger and stranger than the one we started with. And it comes with a peculiar emotional aftertaste. It tells you that your universe is not special after all, not chosen, not favoured. It is merely survivable, one of the rare draws that happen to permit observers, no more meaningful than any winning lottery ticket. That is a strange kind of comfort, if it is comfort at all. The mystery lifts, but so does any sense that we were meant to be here. And here is the fair question that any skeptic will ask, and should ask. Is this science, or is it a story physicists tell to make themselves feel better about a number they cannot explain? If we can never observe the other universes, what is the difference between a multiverse and simply saying we got lucky and refusing to look further? That is a powerful objection, and it would be dishonest to wave it away. So before we go further, we have to ask whether the multiverse has ever done the one thing that separates science from storytelling. We have to ask whether it has ever actually predicted anything, whether reasoning from all these unseen universes ever told us something about our own that we could go out and check. Remarkably, once, it did. And that one prediction is where we turn next. Part 10. The one time the guess came true. In 1987, a physicist used the idea of the multiverse to predict a number before anyone had measured it, and 11 years later, the universe agreed with him. This is the single most important episode in the whole debate, because it is the one time that reasoning from our own existence stopped being a comfortable story and became a genuine scientific prediction, one that could have been wrong and was not. The physicist was Steven Weinberg, one of the great figures of 20th century physics, and the number was the very one we spent the hardest part of tonight on, the energy hidden in empty space, the cosmological constant. Here is the situation Weinberg faced. The vacuum energy, as we saw, was a catastrophe for theory. The naive calculation gave a value larger than anything the universe could survive, off by that factor with 120 zeros. Most physicists at the time assumed the resolution would be simple in shape, even if they could not find it. They assumed that some undiscovered principle, some hidden symmetry, would force the vacuum energy to be exactly zero, cancelling it perfectly, so that empty space would have no energy at all. Zero is a clean, natural answer. It is the kind of value a law can enforce. So the expectation was that when we finally measured the cosmological constant, we would find it to be nothing, precisely nothing. Weinberg reasoned differently, and he reasoned from the multiverse. Suppose, he said, that the vacuum energy is not fixed by any law, but instead varies from universe to universe, across a great ensemble, taking all sorts of values. Then in most universes, it would be enormous, and those universes would tear themselves apart before forming anything, and they would contain no observers. Only in the rare universes, where the vacuum energy happened to be small, would galaxies and stars and observers be able to form. So the question is not what value the vacuum energy naturally takes, but what value observers should expect to measure, given that they can only exist where it is small enough to permit them. And Weinberg worked out that boundary. He calculated the largest the vacuum energy could be while still allowing galaxies to form at all. His conclusion was that if the constant is selected this way, we should not expect it to be zero. We should expect it to be small but not quite zero, sitting somewhere near the largest value still compatible with galaxies existing, because there are more ways for it to be large than to be small, so it should be pushed up against the edge of what life permits. This was a real prediction, and it cut sharply against the prevailing expectation of exactly zero. And then, in 1998, two independent teams of astronomers, studying distant exploding stars, to measure how the expansion of the universe was changing, discovered something that shocked the field. The expansion of the universe is not slowing down, as everyone had assumed gravity would eventually make it do. It is speeding up. Something is pushing space apart, gently but relentlessly, accelerating the expansion, and that something behaves exactly like a small, positive vacuum energy, a cosmological constant that is not zero, but tiny. The measured value came out close to the range that Weinberg's reasoning from the multiverse and the requirement that observers exist had pointed to a decade earlier. The discovery would go on to earn a Nobel Prize, and it left the physics community with a very uncomfortable thought. The one time anyone had used anthropic reasoning across a multiverse to predict a specific number in advance, the prediction had come true. It is worth being precise about what happened in 1998, because the human side of it matters. Two rival teams of astronomers, working separately and in competition, had set out to measure how fast the expansion of the universe was slowing down. They both expected to find deceleration. The only question was how much. They studied a particular kind of exploding star, a type that always detonates with nearly the same brightness, so that its apparent dimness reveals how far away it is and how far back in time you are seeing it. When both teams assembled their measurements, the distant explosions were fainter than they should have been, which meant those stars were farther away than a decelerating universe could account for. The expansion was not slowing, it was speeding up. Both teams, checking and rechecking, arrived at the same disorienting conclusion, and the thing driving the acceleration was given a name, dark energy, which is in effect the vacuum energy we have been circling all night, the cosmological constant, small and positive and real. None of the astronomers making that measurement had set out to test the multiverse. They were simply weighing the cosmos. But the number they found landed close to the range that Weinberg's anthropic reasoning had marked out years before, and that coincidence has hung over the field ever since. It did not prove the multiverse. Nothing so far can. But it meant the multiverse had done the one thing a mere story can never do. It had risked a real prediction about our own universe in advance, and the universe had not contradicted it. I want to be careful not to oversell this, because the channel does not do that, and the argument has its critics. The prediction was not a precise bullseye. It was a rough expectation of the right size and the right character, small and non-zero rather than exactly zero, and there is legitimate debate about how much weight it can bear. But even granting all the caveats, it remains genuinely remarkable, because it is the one place where the multiverse stopped being purely a way to explain away a coincidence after the fact, and instead stuck its neck out and told us something about our own universe before we looked. For a lot of physicists, that is the moment the multiverse earned a seat at the table, however reluctantly they offered it. There is also a second, very different way to get an ensemble of universes with varying constants, one that does not lean on observers at all, and it deserves a mention because it shows how strange the possibilities get. The physicist Lee Smolin proposed, back in 1992, that new universes might be born inside black holes. Every time a black hole forms, on this idea, it buds off a new baby universe on the other side, with constants that are slightly, randomly changed from its parents, like offspring inheriting mutated traits. Universes that are good at making black holes would therefore have more offspring, and those offspring would tend to be good at making black holes too. So over countless generations, the population of universes would come to be dominated by ones tuned to produce black holes in abundance. And here is the intriguing part. Making a lot of black holes requires a lot of massive stars, and massive stars require much of the same chemistry that life does, carbon and long-lived nuclear burning and the rest. So a universe optimized blindly for black holes ends up looking a great deal like a universe optimized for stars and carbon, which is to say, like ours, with no reference to observers needed at all. What makes Smolin's idea unusual, and scientifically respectable, is that it sticks its neck out. It predicts that our constants should be nearly optimal for making black holes, so that nudging any of them should reduce the black hole count. That is a claim you can actually test and potentially prove wrong, which is more than most multiverse ideas can say, even if it remains speculative and contested. So, the road of chance is not empty of real science. It has made at least one prediction that came true, and it has at least one version that is honestly falsifiable. But it also carries an unsolved problem at its center, one we should not hide. To reason about a multiverse, you have to be able to compare its universes, to say what a typical observer should expect to see. And when the number of universes is infinite, comparing them requires a way to weigh one infinity against another, and no one has found an agreed way to do it. This is called the measure problem, and until it is solved, the multiverse cannot cleanly calculate what we ought to observe, which blunts the very predictive power that Weinberg's success seemed to promise. The road of chance goes somewhere real, but it does not yet reach a destination. And so, with law having circled back into chance, and chance leading to genuine but unfinished science, we come to the third and final road, the one physics is most reluctant to walk, the one it will not use even though it cannot rule it out. Part 11. The answer physics is not allowed to use. There is an answer to the fine-tuning of the universe that almost everyone thinks of first, and that physics deliberately sets aside. And understanding why it is set aside tells you something important about what science is and is not. The answer is design. If you show most people the catalogue we have walked through tonight, the balanced nuclear force, the carbon resonance, the weakness of gravity, the impossibly small vacuum energy, the ordered beginning, and you tell them all of it was necessary for us to exist and none of it is explained, a great many of them will arrive immediately at a single thought. It looks arranged. It looks chosen. It looks as though something set the dials on purpose, with us in mind. That reaction is ancient and deeply human, and it is worth stating fairly rather than dismissing, because even great physicists have felt its pull. We already heard Fred Hoyle say that the facts looked as though a superintellect had monkeyed with the physics. Freeman Dyson, another distinguished physicist, once wrote that the more he examined the universe and the details of its architecture, the more evidence he found that the universe, in some sense, must have known we were coming. The argument, laid out plainly, runs like this. The constants look chosen. Things that look chosen usually have a chooser. Therefore, the universe may have been set up deliberately to permit life. It is intuitive, it is old, and it cannot be simply laughed off, because the appearance it points to, the appearance of tuning, is real. We have spent an hour establishing that it is real. So why does physics refuse to use it? Not because scientists are hostile to it, and not because it has been disproven, but for a reason that goes to the core of what makes something a scientific explanation. A scientific explanation has to stick its neck out. It has to predict something specific, something that could turn out to be wrong so that you can go and check. The design answer does not do this. It predicts nothing in particular. Whatever we had found, however the dials had been set, the same reasoning could be applied after the fact to say it was arranged that way on purpose. An explanation that can absorb any possible observation, that fits any universe equally well, tells you nothing about which universe you are actually in. It also does not say how the tuning was implemented, by what means, through what mechanism. And it invites an obvious regress, because if a finely arranged universe requires a designer to explain it, then the designer, being at least as intricate as what it made, would seem to require an explanation in turn, and you have not closed the question, only moved it somewhere you can no longer examine. So physics brackets the design answer. It does not declare it false. It sets it gently aside as something science cannot test, and keeps looking for mechanisms it can. It is worth being clear that this is not a sneer at anyone who finds the design reading compelling. It is a statement about the tool, not about the person holding it. Science is a specific instrument with a specific limitation. It works by making guesses that could fail a test, and then running the test. That is the whole of its power and the whole of its modesty. A claim that no possible observation could ever count against is not thereby false. It is simply outside the reach of this particular instrument, the way a telescope cannot weigh you, and a scale cannot show you the moons of another planet. The design inference asks a question that may be entirely real and entirely important and still lie beyond what a test can settle. Physics does not get to rule on it. Physics only gets to say, honestly, this is where my methods stop. And there is a further reason physicists hesitate, beyond untestability, which is the regress we touched on a moment ago. If the intricacy of the universe cries out for a maker, then the maker, being at least as intricate as the thing it made, would seem to cry out just as loudly for an explanation of its own. You have not ended the chain of why, you have added a link to it and moved the loose end somewhere you can no longer examine. That does not disprove the idea, but it does mean the idea does not do the one job it was brought in to do, which was to make the wondering stop. The same fate meets the modern, secular cousin of the design idea, the simulation hypothesis, put forward by the philosopher Nick Bostrom in the early 2000s. The thought is that if advanced civilizations can build detailed simulations of whole universes, there might be far more simulated realities than real ones, and we could well be living inside one. On this view, the constants of our world would be parameters, settings chosen or randomly generated by whoever wrote the simulation, and the tuning would be a design choice made by a programmer rather than by a deity. It is a genuinely interesting idea, and it reframes the puzzle in a way that feels modern. But as an explanation for the tuning, it has exactly the same strengths and the same fatal weakness as the older design answer. It can accommodate anything, and so it predicts nothing, and there is currently no way to test it, though some have speculated about hunting for computational limits woven into the fabric of reality. As physics, it remains a thought experiment. And at the far edge of respectable physics sits an even stranger notion, John Wheeler's idea of a participatory universe, in which observers do not merely find themselves in a life-permitting cosmos, but somehow help bring it into being through the act of observation. It comes from a serious and brilliant physicist, and most of his colleagues regard it as philosophy rather than testable science. Now here is the pivot that ties this whole night together, and it comes back to that phrase I asked you to hold. Only the hits can look back. Think about what that phrase really implies, because it is the reason design and the multiverse are locked in a stalemate that physics cannot yet break. A universe finely arranged by a designer, and a universe that is one lucky draw among countless others, would look exactly the same from the inside. Both would present you with a set of dials that appear perfectly set for your existence. In the design story, they were set on purpose. In the multiverse story, they were set by chance, and you are simply at one of the rare hits. But the observer, standing inside either one, sees the identical thing, a cosmos that fits. That is precisely why physics cannot choose between them by looking around, because looking around gives the same answer in both cases. Only the hits can look back, whether the hit was aimed or accidental. The appearance of purpose and the appearance of luck are, from where we stand, indistinguishable. And this is where intellectual honesty demands one more turn, the hardest one, because we have to ask whether the tuning is even as severe as I have made it sound. I have spent the night moving one dial at a time, holding everything else fixed, and showing you that small changes are catastrophic. But some physicists point out that this one-at-a-time method may exaggerate the problem. If you allow several of the constants to change together, rather than nudging just one, you sometimes find that a different combination can also produce stars, chemistry, and complexity of some kind. The physicist Victor Stenger argued along these lines, and studies of stars by physicists such as Fred Adams have found that stars of some sort can form across a surprisingly wide range of the constants. The windows may be wider than the single-dial picture suggests. There is a deeper worry still. To say a value is improbable, you need to know the range of values it might have had and how likely each one was. And we have exactly one universe and no theory that tells us how the constants were assigned. We may be calculating the odds of a hand of cards without knowing what deck it was drawn from, or whether there was a deck at all. And there is the quiet assumption that life must resemble us, must need carbon and water, and these particular chemistries, when perhaps some wholly different form of complexity could arise under wholly different settings. In universes we are too provincial to imagine. None of that makes the tuning go away. The vacuum energy is still balanced to more than 100 decimal places, and no amount of adjusting other dials together softens that by much. But it does mean we should hold the whole question with humility and resist the pull to certainty in any direction. And so we arrive, honestly, at the edge of what physics can currently say. Here is the discipline that mapped the inside of the atom and weighed the distant galaxies, and traced the universe back to its first fraction of a second, arriving at the question of why the whole thing fits us so well, and falling quiet, not in triumph, with an answer in hand, not in defeat, throwing up its hands, but in something more like honest silence, standing at the exact boundary of the knowable and refusing to pretend it can see past it. There is a strange and genuine peace available in that silence, if you let yourself feel it, the permission to stand before the largest question there is, and simply not know, and to find the not knowing beautiful rather than frightening. That is the rarest thing this subject offers, and it is worth more than any premature answer. Part 12. The balance you are standing on. Come back now, out of the wide abstractions, into the room where you actually are. It is dark, or nearly so. You are lying still, or sitting still, somewhere on the surface of one small planet, and the ordinary world is close around you, the weight of your own body, the quiet, the slow rhythm of your breathing. I want to end the night, not out among the multitude of universes, but right here, because everything we have talked about is not really out there. It is in here, in this room, holding you together as you rest. Feel the surface beneath you holding you up. It holds you because the force between the atoms in it is exactly as strong as it is. The electric force that keeps solid things solid, set on its dial to the value that lets matter be firm instead of collapsing or drifting apart. Feel the faint warmth that reaches you, first or last, from the sun, the star that has burned steadily for over 4 billion years and will burn for billions more. It burns that slowly, that patiently, only because gravity is almost unimaginably weak enough to give the universe the long, unhurried stretches of time that made a night like this one possible. The light that warms you left the sun about 8 minutes ago and crossed all that empty space to reach you, and it crossed empty space that is quiet and stable, because the energy hidden in that emptiness is smaller than it had any right to be, small enough that space never tore itself apart. Feel your own hand, wherever it is resting. The atoms in it hold together because a nuclear force landed inside a window a few thousandths wide. The carbon woven all through it exists because a single energy level inside a nucleus fell exactly where it needed to fall, a place a man once found by reasoning from the fact that he was alive. The very fact that you can remember this morning but not tomorrow morning, that your night has a before and an after, that time carries you gently forward instead of standing still, all of it rests on the almost perfect order the universe began in, the most improbable condition anyone has ever measured. You are not separate from the tuning. You are made of it. Every one of those dials is set, right now, to the value that allows you to lie here and breathe and drift. Let yourself feel how quiet it all is. None of these forces announce themselves. The nuclear glue holding your atoms together makes no sound. Gravity keeps its patient hold without effort or strain. The energy in the empty space around you sits so gently balanced that you would never know it was there, and yet it is there, and its gentleness is the reason the room is calm rather than flying apart. Everything that had to go right for this moment to exist has already gone right, long ago, and it is still holding, steadily, without needing your attention. You do not have to do anything to keep the balance. It keeps itself. It has kept itself since long before you were born. There is a kind of rest available in that, if you want it. All night we have been looking at how precarious it all seems, how narrow the windows are, how easily it might have come to nothing. But from inside this room, in the dark, the precariousness turns into something more like a held note, a long steadiness underneath everything, the same settings that lit the first stars, still making the warmth on your skin. You are resting on a balance that has never once faltered in the whole life of the universe. Notice, too, that you did not have to earn any of this. You did nothing to deserve a universe that holds together, and you could have done nothing to lose it. It was already arranged, long before there was anyone to be grateful or afraid, and it will go on being arranged long after tonight is forgotten. There is a mercy in that, of a strange and impersonal kind. Whatever the reason, if there is a reason at all, the balance does not depend on you to hold it. You are free, tonight, to simply be held by it, and no one can tell you why. That is the honest truth we carry out of tonight, and I think it is better to carry it honestly than to pretend otherwise. We walked the 3 roads. We followed law, the dream that the numbers had to be what they are, and watched it circle around into a near infinity of possibilities, instead of the single forced answer we hoped for. We followed chance, the multiverse, and found that it dissolves the mystery at the price of an unseen infinity of other universes, and that it once, remarkably, predicted a real number, and that it still cannot fully close its own accounts. We followed design and found that physics cannot use it and cannot refute it, because a made universe and a lucky one look identical from the inside, since only the hits can look back. Luck, law, selection, or something with no name. Those were the 4 possibilities we named near the middle of the night, and after everything, they are still the 4 we are left holding. Not as a menu to choose from confidently, but as an honest measure of how much remains open. I find that I do not want to tell you which one is true, and not only because I cannot. I think the not knowing is the right place to rest tonight. The universe fits us. That much is real and precise and strange, and no serious person disputes the fit. Why it fits, whether by accident or by law, or by selection or by some reason we are not yet able to imagine, is a question that physics has carried right up to its own edge and set down gently, unable for now to carry it further. And there is no shame in that. It may be the most honest thing a science can do, to map exactly how far the light reaches, and then to stand quietly at the border of the dark, without inventing shapes to fill it. So let the question stay open as you let yourself go. You do not need it answered to sleep. Somewhere far above this room, past the ceiling and the sky and the thin edge of the air, the universe goes on holding its impossible balance. Every dial steady, the whole delicate arrangement neither explained nor disturbed by our wondering about it. It held that balance for billions of years before you were here to notice, and it will hold it long after tonight. And you are one small, warm, breathing piece of the one arrangement of matter this universe knows how to build, resting for a while inside the only kind of cosmos that could ever have built you. Whatever set the dials, they are set. The balance holds, and you can let the whole enormous question go for now, and simply rest inside the answer that you already are.